All right, buckle up, everyone, because today we're diving headfirst into the wild world of quantum computing.
Should be fun.
It seems like every time you turn around, there's another headline screaming about quantum computers changing the world as we know it.
It is a pretty hot topic these days, yeah.
But let's be honest, most of us are still trying to wrap our heads around exactly what this quantum stuff is all about. So that's where you come in. You're the expert here to guide us through this quantum jungle.
Happy to help demystify things a bit. I always say the first step is to understand the fundamental difference between our good old-fashioned computers and these new quantum machines.
All right, lay it on me. What's the secret sauce that makes quantum computing so special?
It all boils down to how they process information. Classic computers use bits, which can be either a 0 or a 1, but quantum computers use these things called qubits.
Qubits, huh?
Yeah.
Sounds futuristic.
They are pretty amazing. The thing is, qubits can be a 0, a 1, or both at the same time.
Wait, hold on. How can something be in two states at once? That's like saying a light switch can be both on and off simultaneously.
That's where things get a little mind-bending. It's a concept called superposition, and it's one of the key principles behind the power of quantum computing.
Okay, I'm intrigued, but my brain's already starting to hurt. So a qubit can be in this blurry in-between state. What does that actually mean in terms of computing power?
Think of it this way. Instead of tackling one calculation at a time, a quantum computer can explore tons of possibilities all at once, simultaneously.
Ah, I see. It's like having a massive parallel processing system. So for certain problems, quantum computers could be insanely faster than anything we have today.
Exactly. That's why people are so excited about the potential for quantum computing in fields like medicine, material science, even finance.
Okay, so we've got these qubits doing their multitasking magic. But I've also heard this other term thrown around, entanglement.
Ah, yes, entanglement. It's another essential piece of the quantum puzzle, and it's where things get really wild.
Wild in what way?
Imagine you have two of these qubits linked together in a special way. Now, even if you separate them by a huge distance, what happens to one instantly affects the other.
Like, if one qubit changes its state, the other one flips to match it, no matter how far apart they are.
Exactly. It's like they're connected by some invisible force that transcends space and time. Einstein famously called it spooky action at a distance.
Okay, that's officially blowing my mind. So it's more than just a cool science trick. This entanglement thing actually has implications for things like communication, right?
Definitely. This interconnectedness is what researchers are hoping to harness for building ultra-secure communication networks. The idea is that because of entanglement, any attempt to eavesdrop would instantly change the state of the qubits, alerting both the sender and receiver that something's fishy.
So it's like a built-in alarm system for your data. Pretty ingenious. But every superhero has a weakness. What's the kryptonite for our amazing qubits?
Well, their biggest challenge is something called decoherence. Remember how we talked about a qubit being in that delicate superposition state?
Yeah, both 0 and 1 at the same time.
Right. Well, the problem is that qubits are super sensitive to their environment. Any kind of disturbance, even the tiniest vibration or temperature change, can cause them to decohere and lose that special quantum state.
So it's like their connection to the quantum realm is super fragile and can break easily.
Exactly. It's a bit like trying to balance a spinning coin on its edge. Any little nudge will make it topple over. And when a qubit decoheres, it basically turns back into a regular old bit, losing its quantum superpowers.
Ah, so that's the catch. We've got these incredible qubits with their mind-bending abilities, but keeping them stable long enough to actually do useful computations is a huge hurdle.
It's a massive challenge. Researchers are working on a lot of different strategies to tackle this problem. One approach is to create super isolated environments for the qubits, like ultra-cold refrigerators or vacuum chambers, to shield them from any kind of external interference.
So it's like trying to build a fortress of solitude for these delicate quantum particles.
That's a great way to put it. And then there are also sophisticated error correction techniques being developed to try and detect and fix errors as they occur, kind of like a spell checker for quantum computations.
Okay, so we've got these qubits with their amazing powers of superposition and entanglement, and scientists are working hard to protect them from decoherence. But how do we actually go from these tiny quantum particles to building a real functioning quantum computer?
That's where things get really ingenious. It's all about finding clever ways to manipulate those qubits and make them dance to our tune.
Okay, I like where this is going. Tell me more about how we make these qubits dance.
There are actually a few different approaches being explored. One of the most promising involves using something called superconducting circuits. These are basically loops of wire that are cooled down to extremely low temperatures where they exhibit these weird quantum properties.
So it's like we're using super chilled wires to create a playground for our qubits to do their thing.
That's a good analogy. And because we understand how electricity works so well, we can use these superconducting circuits to control the qubits with a high degree of precision.
Okay, so superconducting circuits are like one way to build the foundation of a quantum computer. Are there any other approaches?
Yeah, there are actually a few other contenders out there. Another really fascinating approach is using trapped ions. Basically, we're talking about trapping individual atoms using lasers and then using those lasers to manipulate the quantum state of the ions.
So it's like using lasers to play a microscopic game of quantum billiards.
Exactly. And because ions are naturally isolated from their environment, they tend to maintain their quantum states for longer periods, which is a huge advantage.
Okay, so we've got superconducting circuits, trapped ions. It sounds like building a quantum computer is a bit like a high-stakes engineering competition with different teams vying for the best approach.
It is a bit of a race, and it's still early days, so it's hard to say which approach will ultimately win out. But the fact that there are so many brilliant minds working on this problem is incredibly exciting.
It definitely feels like we're on the cusp of something truly revolutionary. Okay, so we've got our qubits housed in these super advanced setups, but how do we actually give them instructions? Do they understand binary code like our regular computers?
That's a great question. And the answer is not exactly. Instead of the usual zeros and ones, we use something called quantum gates to manipulate the qubits. These gates are like the logic gates in your computer, but instead of simple AND or NOT operations, they perform these mind-bending quantum operations that exploit the properties of superposition and entanglement.
Okay, so quantum gates are like the conductors of our qubit orchestra, directing their movements and interactions.
I like that. And just like a musical score guides an orchestra, we use quantum circuits, which are sequences of these quantum gates, to create complex algorithms.
So instead of writing lines of code, we're essentially choreographing a dance for our qubits. It's a whole new way of thinking about information processing.
Exactly. It's like we're stepping into a new dimension where the rules of classical computing no longer apply, and that opens up a whole universe of possibilities.
This is where things start to get really interesting. So we've got our qubits, our quantum gates, and our quantum circuits. But what can we actually do with this quantum power? What kind of problems can these quantum algorithms tackle that our classical computers struggle with?
That's the million-dollar question, and the answer is a lot. But maybe we should save that discussion for our next deep dive session.
You're right, we've covered a lot of ground already, and I think our audience needs a little time to digest all this mind-bending quantum information. So stay tuned, folks, because in our next session, we'll explore the exciting world of quantum algorithms and how they could revolutionize everything from cryptography to drug discovery. See you then. Welcome back, everyone. I hope you've had a chance to recover from our mind-bending journey into the world of qubits and quantum mechanics.
I hope so too. Quantum concepts can definitely take some time to wrap your head around.
They sure can. But that's what makes this so fascinating, right? It's like exploring a whole new universe of possibilities.
Oh,
So last time, we left off talking about how quantum computers are built and how they use those mind-blowing concepts of superposition and entanglement.
right. We covered some of the basic building blocks like qubits and quantum gates.
But now I want to know what we can actually do with these quantum machines. What kind of problems can they solve that our classical computers just can't handle?
That's the question everyone's asking. And the answer is a lot. Quantum computers have the potential to revolutionize a wide range of fields, from medicine and material science to finance and artificial intelligence.
Okay, so let's dive into some specific examples.
Yeah.
What are some of the low-hanging fruits where we're already starting to see quantum computers making a difference?
One area that's really exciting is drug discovery. You know how developing new drugs is a long and expensive process?
Oh yeah, tons of trial and error, lab tests, clinical trials. It can take years, even decades, to bring a new drug to market.
Exactly, and it's incredibly costly. But imagine if we could use quantum computers to simulate how different drug molecules interact with the body at the atomic level.
So instead of relying on real-world experiments that take forever, we could use quantum simulations to test out thousands of potential drug candidates virtually in a fraction of the time.
Precisely. We could identify the most promising candidates much faster and eliminate a lot of the dead ends. That would not only accelerate the drug discovery process, but also make it much more affordable.
Wow, that would be a game changer for the pharmaceutical industry. What about materials science? How could quantum computers help us design better materials?
Think about things like solar panels, batteries, or even superconductors. The properties of these materials are determined by the complex interactions of their atoms and electrons.
And those interactions are governed by the laws of quantum mechanics, which our classical computers struggle to simulate accurately.
Right. But quantum computers are uniquely suited for this task. They could help us design materials with specific properties, like higher efficiency or greater durability, by simulating those quantum interactions with incredible precision.
So we could potentially design new materials with properties we never even thought possible before.
Exactly. It's like having a virtual lab where we can experiment with different atomic arrangements and see how they affect the material's properties.
Okay, so I've got drug discovery, materials science. What other areas are ripe for quantum disruption?
Well, optimization problems are another area where quantum computers have the potential to outshine classical computers.
Optimization problems.
Yeah.
Can you give me an example of what you mean by that?
Think about something like finding the most efficient route for a delivery truck that has to make multiple stops.
Oh, yeah. Or maybe figuring out the optimal way to allocate resources in a complex supply chain.
Exactly. These kinds of problems can have a huge number of possible solutions, and finding the best one can be incredibly time consuming for a classical computer.
Especially as the number of variables grows, it becomes exponentially harder to find the optimal solution.
Right. But quantum algorithms can leverage superposition and entanglement to explore multiple possibilities simultaneously, allowing them to find the best solution much faster.
So they're like master puzzle solvers that can cut through the complexity and find the most efficient solution in a fraction of the time.
That's a great way to put it. And this has implications for all sorts of industries, from logistics and transportation to finance and manufacturing.
Okay, this is all incredibly fascinating. But I have to ask, what about those more futuristic applications we hear about, like quantum cryptography and the quantum internet? Are those still just pipe dreams?
They're definitely still in their early stages of development, but progress is being made all the time. Quantum cryptography, with its promise of unhackable communication, is already being tested in real world settings. And researchers are working on building the building blocks of a quantum internet, which would be a game changer for secure communication, scientific collaboration, and more.
A quantum internet. It's mind-boggling to think about what that could enable. But let's shift gears for a moment and talk about something a little more practical. I know a lot of our listeners are probably wondering how they can actually get involved in this quantum revolution.
That's a great point. And the good news is you don't need a lab full of expensive equipment to start exploring quantum computing. There are some fantastic online platforms that make it accessible to anyone with an internet connection.
Really? So I could potentially learn about quantum computing and even write my own quantum algorithms from the comfort of my home.
Absolutely. One of the most popular platforms is the IBM Quantum Experience. It gives you access to real quantum computers that you can program and run experiments on, all for free.
Wow, that's incredible. So there's no barrier to entry. Anyone could just jump in and start exploring.
Pretty much. They have tons of tutorials and resources to help you get started, even if you're a complete beginner. And there are other platforms out there too, like Amazon Bracket, which gives you access to a wider range of quantum computing technologies.
Okay, so we've got these amazing platforms making quantum computing accessible to the masses. But let's be realistic for a moment. Quantum computers are still in their early stages of development, right? What are some of the limitations we're facing right now?
You're right. Quantum computing is still a young field. One of the biggest challenges is scalability. Building larger and more powerful quantum computers is incredibly difficult.
Because of those pesky decoherence issues we talked about earlier.
Exactly. The more qubits you have, the harder it is to protect them from the environment and keep them in that delicate quantum state.
So it's a balancing act. You want more qubits for more processing power, but the more you have, the harder it is to keep them stable and coherent.
That's the challenge. Researchers are working on a lot of clever error correction techniques and ways to isolate the qubits from any kind of disturbance, but it's a tough engineering problem.
And then there's the issue of cost, right? Building and maintaining these quantum systems is incredibly expensive.
Yes, that's another hurdle. But the good news is that the cost is coming down as the technology matures. And with the rise of cloud platforms, you don't need to own a quantum computer to experiment with it.
So even though we're not quite at the point where everyone has a quantum computer on their desk, the technology is becoming more and more accessible.
Exactly. And I think that's really important because the more people who get involved in this field, the faster we'll make progress.
So it's like a collective effort to push the boundaries of what's possible with quantum computing. But before we wrap up this part of our deep dive, I think it's important to acknowledge that with any powerful new technology, there are potential risks and ethical considerations that we need to be mindful of.
You're absolutely right. We need to have open and honest conversations about the potential impact of quantum computing on society and ensure that it's developed and used responsibly.
For example, we've talked about the potential for quantum computers to break current encryption methods. What steps are being taken to address that?
That's a huge area of focus right now. Researchers are working hard to develop new quantum resistant encryption algorithms that can withstand attacks from even the most powerful quantum computers.
So it's like a race against time to ensure that our data remains secure in a post-quantum world.
It is. But it's not just about cybersecurity. We also need to think about the potential impact on employment. As quantum computers become more capable, they could automate tasks that are currently done by humans.
So we need to start thinking now about how we can prepare the workforce for the changes that quantum computing might bring.
Exactly. We need to invest in education and training programs that equip people with the skills they'll need to thrive in a quantum powered economy. And we need to think about how we can ensure that the benefits of this technology are shared broadly, not just concentrated in the hands of a few.
It's a reminder that technology is never neutral. It has the power to shape society in profound ways, and it's up to us to make sure that it's used for good.
I completely agree. We need to be thoughtful and proactive in how we approach the development and deployment of quantum technologies. But I'm optimistic that if we do it right, quantum computing has the potential to solve some of the world's most pressing challenges and create a brighter future for all of us.
Okay, so we've gone pretty deep into the world of quantum computing, but I have a feeling we've only scratched the surface of what quantum technology can do.
Yeah, you're right about that. Quantum computing is just one piece of the puzzle. There's a whole universe of other quantum technologies out there.
A whole universe, huh? Makes space travel sound easy. But seriously, what else is out there besides quantum computing?
Well, we touched on quantum cryptography and communication earlier, but one area that's really taking off is quantum sensing.
Okay, quantum sensing. Now that sounds intriguing. What's that all about?
Basically, quantum sensing uses the extreme sensitivity of quantum systems to detect even the tiniest changes in their environment. Think of it like having a microscope that can see things at the atomic level.
Wow, so we're talking about sensors that are way more precise than anything we have today.
Oh, yeah, by orders of magnitude, they can pick up on things that are completely invisible to our current technologies.
Okay, I'm picturing some kind of super-powered magnifying glass.
Yeah.
But how would we actually use these quantum sensors in the real world?
The possibilities are endless. In medicine, for example, quantum sensors could revolutionize diagnostics. Imagine being able to detect cancer cells at their earliest stages or monitor brain activity with incredible precision.
So we're talking about diagnoses that are not only more accurate, but also far less invasive than current methods.
You got it. And that's just the tip of the iceberg. Think about environmental monitoring. Quantum sensors could detect pollutants in the air and water at incredibly low concentrations, helping us protect our planet.
From healthcare to environmental science, quantum sensing sounds like a game changer. What about quantum communication? We talked about unhackable communication, but is there more to it than that?
Definitely. Unhackable communication is a huge deal, but quantum communication also allows us to transmit information in ways that are just impossible with classical methods.
Like that quantum teleportation thing you mentioned earlier. The idea of instantly transferring quantum states across vast distances still blows my mind.
I know, right? It sounds like science fiction, but researchers are actually making progress towards building the building blocks of a quantum internet.
A quantum internet. Okay, now you're really messing with my brain.
Mm.
But seriously, how could we even build something like that?
Well, it would involve connecting quantum computers around the world, creating a network where quantum information can be shared and processed at lightning speeds.
So instead of sending emails and making Zoom calls, we'd be beaming quantum data packets around the globe.
You got it. It's a wild idea, but the implications are huge. Imagine being able to conduct scientific experiments in real time with collaborators on the other side of the world, or having instant access to medical data and expertise no matter where you are.
It's like something straight out of Star Trek. So we've got quantum sensing, quantum communication, a potential quantum internet. Feels like we're on the verge of a technological revolution that could dwarf anything we've seen before.
It really does, and we're just getting started. There are so many mysteries left to unravel in the quantum realm. Who knows what incredible discoveries and innovations await us?
It's exciting and a little bit scary all at the same time.
But that's the beauty of science, right? It's constantly pushing the boundaries of what we thought was possible.
Couldn't have said it better myself. And that's what I find so inspiring about the field of quantum technologies. It's a constant reminder that there's still so much to learn and discover about the universe.
Well, I think it's safe to say that you've officially blown my mind with all this quantum talk. We've journeyed from the mind bending world of qubits and algorithms to the far reaching possibilities of quantum sensing and a quantum internet. It's been a wild ride.
It's been a pleasure sharing my passion for this field with you and our listeners. And a huge thank you to our listeners for joining us on this deep dive into the quantum realm.
Yeah, thank you for listening, everyone. We hope you've learned something new, had your mind stretched, and maybe even caught a glimpse of the incredible future that quantum technologies hold for us all.
Who knows, maybe one of our listeners will be the one to make the next groundbreaking discovery in this fascinating field.
Anything is possible.
Until next time, keep exploring the quantum frontier.